Right, question 4, sample paper A is our old friend, the quantum harmonic oscillator. So you've done an awful lot of work on the quantum harmonic oscillator, both in the first semester and the second semester of the quantum world. Your very first coursework exercise last semester was based entirely around the quantum harmonic oscillator. Lots of worksheet questions about the quantum harmonic oscillator. Chapter 7, all about the quantum harmonic oscillator. So it's a core element of this course. It's a core element of physics in general for all the reasons I describe in the videos related to Chapter 7. So it's not unusual that you should see questions about the quantum harmonic oscillator appear in the exam paper. Right. A particle with mass m is confined to a one-dimensional simple harmonic potential given by that, where omega is the classical angular frequency. Starting from the classical expression for the total energy, determine the quantum mechanical Hamiltonian operator for the particle. Right, with two contributions, obviously, kinetic energy and potential energy. Kinetic energy term, that's right, this is our total energy that asks in the question. Don't get confused, throughout the notes I use this to represent potential energy. In this particular case, the question is couching it and saying U is the total energy. So, total energy in this case is going to be the kinetic energy, which is no more than half mv squared, if that's how you prefer to think of kinetic energy, and the potential energy. What's this Springs constant? Well, our angular frequency is given by this. Implies k is equal to m omega squared, which means we can write this as p squared over 2m plus a half k m omega squared, and we've got our x squared. Translating this to quantum mechanics, we have to think about our momentum operator and our position operator. This is our total energy balance, so this represents a Hamiltonian. What's our momentum operator? Well, our momentum operator in one dimension, I should have a little x on this, but we're talking entirely about one dimension in this case, so if you'll excuse me, I'll leave off the little x subscript, but bear in mind that's one dimensional. So, plugging that in there, we have, and let's write this now in terms of Hamiltonian operator. I should stress that the Hamiltonian, I've stressed this before, but I'll stress it again in the context of going through the exam papers. The Hamiltonian is not this magical quantum concept. The Hamiltonian is a classical physics concept as well. It's just about keeping the energy balance. It's about keeping account of the total energy in the system. So, Hamiltonian, plugging that in there, h bar squared over 2m plus a half m omega squared, and our quantum mechanical operator for position is the same as the is just x. So principle, I should put a little hat on there, but in this case I think it's a little bit superfluous to do that, but if you want, put a little hat on there just to remind yourself that that's an operator. Okay, 3 marks, onwards and upwards, or sideways. Next part of the question, show that the Hamiltonian can be written in terms of the scale coordinate q is equal to Lx as that. So when we did the simple harmonic oscillator, we couched everything in terms of natural units, where h bar is equal to m is equal to omega 0 is equal to 1. And beginning towards the start of chapter 7, I explained just how those natural units, we come by those natural units and how we use those natural units, and on the video on the quantum harmonic oscillator potential, I also go through where those natural units come from. In this question, we're not using natural units like we did during the course. This question stems from a number of years back, actually I think as far back as 2014. So I've just kept it in its close to its original form. I have modified other chunks of it, but this particular bit I want to keep close to its original form, just to show you that we don't have to do it the way we did in terms of natural units. There are other ways of scaling. So let's see how they do it in this particular question. So it asks you to recouch the Hamiltonian in that context. So I'll put the Hamiltonian back up here. So we want to recouch this in the context of this variable. So this one's quite straightforward. Let's do this one first. So that implies x squared is equal to q squared over L squared. Implies a Hamiltonian is equal to, we'll get on and do the derivative for x in a second, the second derivative with respect to x in a second, half m omega squared q squared over L squared. So that's our potential energy part of the Hamiltonian done. Let's now focus on this. Okay, Q is equal to Lx implies dq dx is equal to L. What's d dx? So d dx is going to be dq dx. Ultimately, remember we're translating this to d squared dq squared, so that's dq. We know dq dx is equal to L, so that implies d dx is equal to L d dq. Apply that argument again, implies d squared dx squared is equal to L squared d squared dq squared. Right, so now we've couched our potential energy term in terms of Q, and now we've got our derivative and therefore got our kinetic energy term also in terms of Q. So let's rewrite this, plug this in here. So the question tells us that our Hamiltonian is, or they want us to have the Hamiltonian in this form, which is, yeah, Q squared. Why are they doing that? Well, hopefully, the key reason we introduced natural units was to make the physics stand out a little bit more and to make the mathematics much less laborious in terms of the number of constants we had to carry around all the time. In this particular case, I hope you recognise that. Okay, so let's compare and contrast. We can let's just concentrate on the potential energy term. So half, what's this telling us is a half h bar omega q squared is equal to half m omega squared q squared over L squared. Rid of the half, get rid of the half, get rid of one of the omegas as well. So that means that L squared is equal to m omega squared, get rid of q squared obviously as well, over h bar omega is equal to m omega over h bar. So L is going to be the square root of m omega over h bar. Right, so let's plug this in here. Remember, this is L squared at the moment. So we're going to have minus h bar squared times m omega over h bar. Our m's are going to cancel. This is going to become h. We're going to be left with an omega, and we've still got that factor of a half, and so we can see that this is indeed equal to a half h bar omega d squared dq squared, well, minus d squared dq squared. Make sure you can work that out for yourself. Just plug that in and make sure it fits. Okay, next question is this. I really quite like this question because the core of what an eigenvalue problem is all about. Determine the value of beta for which that function is an eigenfunction of the Hamiltonian and find the eigenvalue. C is a constant. Right. Eigenvalue problem. So eigenfunction, eigenvalue. So let's apply our Hamiltonian. And apply that to u, a function. So a Hamiltonian operating on a function, that's what we're going to do. So a half h bar omega q squared minus d squared dq squared c e to the minus beta q squared. very familiar with this type of function at this stage. Let's just take that C outside instead of carrying it around all the time. I'll bring it to the front, bring it to the fore. So we're going to C, and then we've got guts of our operator operating on e to the minus beta q squared. We need to take the first derivative and then the second derivative of this. Stop now and stress this again. I say in the what do I need to know for the Quantum World exam section that I've added to the notes recently, I say be able to do derivatives and integrals of exponential functions and complex exponentials in your sleep. Like that. Because otherwise, if you're flailing around in an exam trying to do differentiation that you should really have, right at your fingertips, you're wasting valuable time and you're wasting valuable marks. So you're going to have to differentiate exponential functions. You're going to have to integrate complex exponentials. Make sure you can do those things. That's a key piece of exam practice before you go in. And you might say, well, of course I can do that. Under pressure in an exam, I've seen lots and lots of issues in terms of differentiation. The mistakes I did make myself and did make myself as an undergraduate. So I keep using the musical instrument thing, and if you're more into sports and the idea of muscle memory, it's almost sort of muscle memory for the brain where you should be able to do these type of things without thinking about them. Having said all that, of course I'm going to screw up the differentiation here, but hopefully not. We need to get the first derivative of this. Right, so chain rule, so that's going to be, take this through, that's going to be minus 2 beta q by our original function. Now we're going to get the second derivative of that, which means getting the first derivative of this implies d squared dq squared operating on this is going to be, okay, so it's a product rule. I don't know how you remember the product rule. I suspect it's something like me. First by derivative of second plus second by derivative of first. So, first by derivative of second, well, we've just done that. It's that. Plus a second, which is our original function. By the derivative of the first, what's the derivative of that? Well, it's going to be minus 2 beta. So that's the kinetic energy part of the Hamiltonian. Then remember, we've also got to add in the potential energy part. So multiplying our functions through by q squared. Let's do that. Actually, let's put the entire, plug what we've just got for the derivative into the Hamiltonian. Okay, I'll fix that with Camtasia just so you can see it a little bit better. Okay. This is our function, this is our function, this is our function, our eigenfunction. Now, we have an issue here. This is an eigenvalue equation. Then what we've got to do is our Hamiltonian acting on our operator has got to give us a constant. So something independent of q multiplied by our original function. Problem here is that we've got q squareds. So we've got something which depends on q. The only way this can be an eigenfunction is if that q square, if these terms actually go to 0. So let me express that a little bit more clearly. So that's q squared minus 4 beta squared into minus 4 beta squared. Sorry, q squared u plus 2 beta u. Okay, so this term's fine because it's constant, independent of q. Oh yeah, that does need to be a bracket there, that's right. But this has got to go to 0 because there can't be a dependence on q. So that means q squared minus 4 beta squared q squared is equal to 0. That implies 4 beta squared is equal to 1. Which implies beta is equal to plus or minus a half. Now, remember going back when I was talking about the ladder operators and the diabolically clever example, as Griffiths puts it, of just how we show that we can't have negative energy eigenvalues. Go back to that. That means that we can throw out the minus a half solution, so we're just left with a half. In other words, our function, our eigenfunction, and this will bring back lots of joyous, happy memories, is some normalization constant times e to the minus q squared. Beta is equal to half, so that's 2. You remember that one. Onwards, upwards. Remaining on the eigenfunction theme. The normalized energy eigenfunctions of the particle correspond to the energy levels En, n equal to 0, 1, 2, etc. Oh, that's the other thing. Don't get confused. I know it's frustrating, and there are reasons we do it like this, as I've explained in the notes and as I've explained in the videos. But for the infinite potential well, for example, and indeed for the finite potential well, square potential well, we label from n equal to 1, n equal to 2, n equal to 3. For the simple harmonic oscillator, the quantum harmonic oscillator, we start off with 0, n equal to 0, n equal to 1, n equal to 2. Just bear that in mind. It's important in terms of realizing what the ground state energy is. So these are our lowest two energy levels, eigenfunctions expressed in Q, in terms of Q. At time t is equal to 0, the wave function of the particle is given by an equal superposition of the two eigenstates represented by the two eigenfunctions. Write down the solution of the time-dependent Schrödinger equation. And then we've got something based on the raising and lowering operators, which I'll get to. Okay, particularly for the second part of this, I'm going to switch to Dirac notation. Now you can follow this through. And you can do exactly what I'm going to do in terms of Dirac notation. You can do it by dragging all those integrals around and looking up the values of those integrals, etc. But what we're going to do, what I tried to really emphasize throughout the module, certainly the latter half of the module, is that by using Dirac notation and exploiting the orthonormality of the eigenfunctions, we can save ourselves so much work. This is a very good example of where this is the case. I would argue that with Dirac notation and exploiting the orthonormality of the eigenfunctions, instead of doing all the integrals brute force, quarter of the time, I'd estimate. If nothing else, instead of having to write down tons and tons of integrals, you can just write down the bras and the kets, and it makes life a lot easier. You might be convinced. I'll try and convince you on this. It's a nice, elegant example of Dirac notation. So, having said all that, superposition with an equal weighting of the first two eigenfunctions. So what we'll have, keeping normalization in mind, what does it ask us to express it as? Okay, I'm just going to express, I'll just express the state vector as psi. We want an equal weighting. With normalization, that means we want 1 over root 2 times our first plus 1 over root 2 times our, well, n equal to 0 eigenstate, n equal to 1 eigenstate. That's at t equal to 0, because there's no time dependence. If we now put it in terms of t, just to explain, 1 over root 2 plus 1 over, these are the coefficients, so if we square those, half plus a half gives us 1, so it's normalized. As described for question 1. Right, now we put in the time dependence. So let me take that 1 over root 2 outside. What we're going to have is our ground state eigenket minus I E0t over h bar plus our first excited state n equal to 1 eigenket minus I E1t over h bar. Right, so that's our state vector. You could write it in terms of wave functions if you like, and have a psi x there. Entirely up to you, but that's our state vector in terms of an equal superposition of the first two eigenstates with the temporal, with the time dependence put in place. 3 marks. Right, the raising and lowering operators, respectively, can be written in terms of Q as follows. Show that the momentum operator can be written in terms of like that, and then subsequently show that the expectation value of momentum at time t is given by that, or omega is equal to that. It even says at the bottom Use of Dirac notation is recommended for this part. Now you don't have to use Dirac notation. If you really want to go through the integrals, that's fine, and you work it all through and out pops the answer at the end, that's fine. But it's recommended. Dirac notation is recommended. Moreover, you note that an awful lot of questions we try to couch where possible. It's not always possible, I'll admit, but where we do try to couch the questions in terms of show that. So you've got a result to work towards, and you can check your working, so it gives you a little bit more confidence if you actually get that show that result. Don't do what sometimes happen, which is in the exam paper, in the exam scripts after marks, sometimes you get show that, and then write down what's in the exam paper. Nonsense, 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 nonsense. Out pops the answer at the end, QED. If you're going to do that, don't put a QED on the end. But we do that to help you. We really, we're not setting these exam papers up to be the most, stressful thing they could be. We're doing that to help you, to sort of guide you in the right direction. So we try to use show that as much as possible. Right, so show that the momentum operator can be written in terms of the raising and lowering operators as follows. We're defining, or in the question it defines the raising operator in terms of Q, maintaining the link with Q, like that, and the lowering operator like that. So elsewhere, in different textbooks, a bit frustrating in terms of notation, in different textbooks, different lecturers, different YouTubers will use a different notation for the raising and lowering operators. I like this notation, which is Griffith's notation, where it's very easy at a glance to go, well, that's the raising operator, that's the lowering operator, plus is going in the plus direction, minus is going in the minus direction. Right, first step is to couch these in terms of P. So we know that our momentum operator is this, which in terms of Q, that's a minus, is minus IH bar L D dq. Just to make things clearer. That's our first step. So that means we can write d dq in terms of P as follows. So that means d dq is going to be 1 over minus IH bar L by a momentum operator. We can take the I up. 1 over I is the same as minus I. So we can then write d dq as, so all we've done is just rearrange. All we've done is just rearrange things. Now we plug that into this. Let's do it for the raising operator. And what we have is our raising operator is going to be minus I H bar L. And similarly, for doing exactly the same thing for the lowering operator, just need to point out this has got nothing to do with normalization. If we had completely different normalization factors, this remains 1 over root 2. It's just how we define, see the notes, it's how we define the raising and lowering operators. So that's our raising operator, that's our lowering operator. So you can see in the question that the momentum operator is defined in terms of the difference of these two operators. So if we subtract one from the other, the reason that is the case is because that means we can get rid of the Q here. So A minus A plus is going to be 1 over root 2. And then we're going to have 2I H bar L P. Because I over H bar L P minus I over H, so it's going to give us twice that. Now we've just got to rearrange this to get the momentum operator in terms of the difference of the raising and, lowering and raising operators. Rearranging, that implies Okay, let's take that. That's root 2 h bar L 2I over 2I times this minus a raising operator. Root 2 goes into 2, root 2 times I comes above, it becomes minus, so minus I h bar L. You can leave it on the bottom if you want, but it's right, which is as given in the question. Final part. Subsequently show that the expectation value of momentum at time t is given by that. Let's go. So we've shown that the momentum operator can be couched in terms of the raising and lowering operators. And remember, the raising and lowering operators are great because they allow us to shift eigenkets up or down one state on the ladder, so we can convert one eigenket into the next, if we use the raising operator into the n plus 1 state, or the lowering operator into the n minus 1 state. That's very helpful. That's why we've done that. That's why we've couched the momentum operator in terms of those raising and lower operators. You don't have to do it that way. You could start off, as I say, from the expectation value integral for momentum and work through that way. It's a lot more work. So, what we have, and what we're trying to find, is the time dependence of that operator. And that is going to be, well, we've worked out what a momentum operator is in terms of the raising and lowering operators. It's that. And we're going to have our state vector minus. So we're going to have this operating on our ket, then we're going to brad, and we're going to see what the result is. And that's going to give us the time dependence of the expectation value, that is a minus, of the momentum operator. Got to remember normalization. We've got to be careful with factors of 2 and root 2. I am awful for dropping factors of 2 and root 2 left, right and centre. It drives me up the wall. I did it when I was writing out the solution of this question. I had to chase it back. So be careful with factors of root 2, 2, and they crop up time and time again, not least because we've only got two states in this case. We've got an equal superposition of the first two eigenstates, therefore our normalization factor is 1 over root 2. Okay, let's divide this up. We're going to get this operator operating on this. We're going to work out this operator operating on this. We're going to subtract the 2. Then we're going to bra that with our state vector and see what we get. That's the strategy. Okay, so lowering operator operating on our state vector, which was, remember, first eigenket e to the minus I e0 t over h bar plus second eigenket e to the minus e1 t over h bar. Right, we're now going to apply the lowering operator to that. And if we apply the lowering operator to the ground state, we can't go any lower, so this becomes 0. If we apply the lowering operator to this, we pull it down one step on the ladder, and what we'll have is 1 over root 2 u0 e to the minus I e1 t over h bar. The lowering operator pulls the eigenstate down, but it doesn't pull the temporal dependence down. It operates only on the eigenket. The normalization factor is just root n is equal to 1, so normalization doesn't have to be taken into account. In fact, we find that in this particular case, just due to the joy of orthonormality, we don't have to care about those normalization factors. It works out without having to care. You can put factors in if you want for the normalization. In the end, they're going to drop out for reasons which will become clear. Okay, so that's what we get when we apply the lowering operator to our state vector. Now let's do it. Now let's apply the raising operator to our state vector. Let's write it out longhand again. So we're applying the raising operator to 1 over root 2 into and then out of chalk again. let's switch to this. Yeah, okay. Hope you don't mind the switch to yellow. And then U1 e to the minus E1 t over h bar. Same thing again, but this time we're applying the raising operator. So if we apply the raising operator, if we apply the raising operator to this, 1 over root 2 U1 e to the minus E0 t over h bar plus U2 e to the minus IE2 t over h bar. Okay, we should in principle put a normalization factor in. I'll put a normalization factor in here because we're going from n equal to 1, n equal to 2, so there should be a normalization factor in here. Let's call that C. As you're going to see, and for hopefully reasons that you can see coming, it's not going to matter. So that's our when we apply a raising operator, that's what we get. We've applied our lowering operator. Now what we want to do is subtract what we got for our raising operator from what we got for our lowering operator, as defined in the by the expression we have for the momentum operator. So when we apply lowering operator and subtract to our state vector, what we get is 1 over root 2, and we'd lowered, so this is minus IE1 t over h bar minus, what did we have, U1 e to the minus I, because we've raised, minus IE0 t over h bar, and then also minus U2, let's put our constant in, e to the minus IE1 t over h bar. Okay, that's what we get when you apply these operators to that. Now what we're going to do is we're going to do this. Remember what our state vector is? That's a bra for state vector. What's a bra compared to a ket? Well, it's the columns go to rows, and importantly in this context, we get the complex conjugate. So a complex conjugate of our state vector, including the temporal dependence, is going to be e to the plus I E0 t over h bar times bra, in this case U0, plus, and there's a 1 over root 2 outside here. There's a 1 over root 2 outside here. Told you I'd nearly drop it. Plus I E1 t over h bar U1 da. So that's our bra. That's our ket when we've operated on it with the appropriate operators. So what we're going to do now is take the bracket of this and this, remembering orthonormality. So when we take, if we have U0, if we have a bracket of U0 and U0, 1. If we have a bracket of U0 and U1, 0. If a bracket of U1 and U2, 0. Anything that doesn't involve the same index disappears. Anything that does involve the same index, 1. Saves an awful lot of integrals and an awful lot of hard, unnecessary work. So if we work that through, and you should convince yourself of this, what we find, working through, taking the inner products, working them out, realizing that only if the index is the same do we get 1, all we're left with in the end is this. A half instead of 1 over root 2, because there's 1 over root 2 coming from the bra, 1 over root 2 coming from the ket, so this becomes a half. And all that's left are those exponential terms. So, which are, let me get this the right way around, e to the I, and then minus I E1, I'll put a plus in there just to highlight that. That's all that's left. And hopefully this type of thing rings a bell. Notice that in the question it defines, and you should realise this anyway, that omega is E1 minus E0 over H bar. Joule second, joules means the unit here, or better in terms of dimensions, is T minus 1, capital T minus 1. So this is a frequency, which is what we'd expect. So we have a half e to the minus I omega t minus e to the I omega t. So that's what this bit is. Our momentum operator has a factor outside, so we need to take account of that. So it's not just this. And what we end up with is equal to minus I H bar L over root 2, which is how it's defined in the question. We've already done all that, so that's minus I H bar L over root 2. There's a factor of a half, stemming from the products of those 1 over root 2's for normalization. Half e to the minus I omega t minus e to the plus I omega t. Let's get rid of this negative, flip that round, so that's I H bar L over root 2. Let's take that factor 2 out here, 2 here, into, flip this round because we got rid of the negative, e to the plus I omega t minus e to the minus I omega t. Right, now we use good old Euler to convert our complex exponentials to a trigonometric form, and what we have is I H bar L 2 root 2. What we had was 2i, and what we have is 2i sine omega t. Make sure you can see that e to the I omega t minus e to the minus I omega t is going to give us that. Get rid of that, get rid of that. I by I gives us a negative 1, so we have minus h bar over L root 2 sine omega t. Done. But what I really like about that is the use of Dirac notation. It really shows you the elegance of Dirac notation, where, I'll say it again, we don't have to do integrals until the cows come home. Okay, that was a long question. Moving on to question 5 of sample paper A. So, should say this, as you know, there were 5 questions on the paper. Some years it's 2 for semester 2 and 3 for semester 1, or vice versa, whatever it was, 2 for semester 1 and 3 for semester 2. And some years it's half and half, in that one of the questions will be divided in 2. We'll see that with equally weighted between semester 1 and semester 2. We'll see that in some of the other sample exam papers. In this particular case, we got 3 questions based on material from semester 1. So let's move on to question 5, last question in this paper.